I would like to introduce Professor Paul Dorbec from University of Caen, Normandy from France. He is a good researcher in discrete mathematics and combinatorial game theory, I think. And today we want to talk about power domination in the graph. Thank you, Paul, for accepting the invitation. Thank you.
Hello, can you hear me?
Yes.
Okay, good. Thank you. So sorry, I couldn't switch on the video before, but I don't know about the picture, I think.
Yeah.
Okay, so we'll try to
Share. Okay.
the screen. You see the slides?
Yes. Yes. It's okay.
Okay. So thank you for the invitation, and I'm happy to virtually be here and so that I can present a survey on power domination in graphs. If you have any question, don't hesitate to interrupt me if I'm not clear or if I try to take some time on the definitions so that everybody can understand. And then I get to some more involved results. Okay. So the motivation for power domination was related to smart grids and on monitoring power grids. I won't go deep into that because I'm not a specialist, but I found this nice picture of from a website where they use some PMUs, and PMU are standing for phasor measurement units. And the problem of power domination is a graph presentation of this problem of placing some phasor measurement units in a power grid. So I will use the picture of one of the first papers referred on the topic, which was from Baldwin, Mealy, Boysen, and Adapa. So they were really physicists considering electrical networks, and they wanted to monitor the whole network from a set of PMU, of phasor measurement units, and using as few PMU as possible. So I've taken the picture here, which is supposed to represent an electrical network, and I suppose I start with two phasor measurement units, one on the 14th bus and one on the 5th bus. And what they claim is this unit allows to measure the state of the place where it is, and together with also the state of the connected wires. I don't know if you can see my mouse moving on the picture or...
Yes, we can see here.
Okay, so I can point. It's good. Thank you. So at first it monitors the wires, and then from the status of a bus and of the wire connected to it, we can infer by the Ohm law the status of the next bus. And then, so there is some knowledge on these vertices. So buses will become vertices from this PMU. And we see here, we started with a simple dominating set. I mean, a simple set of vertices dominated by the blue stars. And then we continue to use the physical laws. And Ohm law allows to, again, infer from the fact that we know the status of the bus number 6 and the bus number 8, we can infer the wire going from 6 to 8. The current going through the wire from 6 to 8. And so we will monitor also this wire, and also the one from 10 to 12 with these two. And then from this, we have now another law in physics known as Kirchhoff law, where, for example, on bus 12, we have the current coming from 2 of the 3 wires connected. So we can infer the wire going from outside of 12 from toward 13, and then infer the status of 13. So we get this way. So somehow I started, so, okay, I don't, so this one, sorry. And this one, on this state, we are stuck. I mean, we cannot infer any low edge from these three or from these three from this part of the graph. Another solution would be to start with this bus 4 and 15. This is a position where we cannot evolve. But if we add the vertex 6 in the set, then we observe that from 5, we know the status of 4, of 6, so the current coming here, and we can infer the status of 10, and then from 14 to 12, and so on. So we make this a graph problem, where we first, so let me put it in a graph. We first choose a set of vertices. There are the light blue vertices. And we dominate all the neighbors. So we say the neighbors of the initial set are monitored. And then iteratively, every time we have one vertex here, for example, whose neighbors are all monitored but one, we consider that this one becomes monitored on its turn. Okay? So I will give some example because it may be not very clear, but we have so the first graph theoretical definition of this problem was introduced in 2002 by people with names start from the H, but many of them are famous. And the first step is the step of domination, where every vertex, where we have selected every selected vertex with a PMU monitors its close neighborhood. And then a step of propagation, where every time we've got this configuration, where we have a non-monitored vertex, and all of its neighbors are monitored, except one, then we add this one into the set of monitored vertices. And we will denote the power domination number, the minimum number of vertices so that the graph becomes eventually completely monitored, gamma p for the power domination number of the graph G. So let me take another example. This is a planar triangulation. And in this example, if I start with these two vertices, I put these two vertices in the set. Then at the first step, I dominate all the neighbors of these two vertices. But what we will observe now is that this is enough to monitor the whole graph. Indeed, already, so I have to choose well, but this vertex here has all of its neighbors monitored except this one. And also, it's also true for this one. So at next step, so I started from this one instead, but this vertex had all its neighbors monitored, blue, except this one. So we will add this green vertex to the blue set. And the same for this one. All of its neighbors were blue, so we will add this green vertex to the blue set. And once we've added these two vertices to the blue set, we have some new identical situations. So for example, now, once these two have been added, this vertex has all of its neighbors monitored except that one, so it will propagate here. And the same for this one will propagate here. So I put these two green vertices again in the blue set. And then these two vertices only have one neighbor not monitored yet. And finally, I dominate everything. So somehow, when I have a power dominating set, I have a set of vertices initially monitored and some oriented tree that shows me how everything will propagate to the full graph. In this tree, we'll use it later, but every vertex has except for the light blue vertices, which I have chosen at the beginning, every blue vertex has only one outgoing edge. Yes. Okay, so it's quite interesting. I want to compute the domination number of a whole family of all the graphs one by one. So well, one thing I can observe with this small example here. So again, I start with these two. I can observe that this one will propagate here, this one here, and this one here. And then when I propagate, I can propagate a second step like this. And then all of these will propagate to the next line. And then all of the next line will propagate to the next line and so on. So what's happening here is with a finite portion of the graph dominated at the beginning, I can have propagation and monitor an unbounded number of vertices from a finite set at the beginning. So somehow it says that it's not likely that we will be able to give a bound on the power dominating set on a general graph, depending on the total number of vertices. Okay. Okay. So if I want a very formal definition, which will be useful because I will define the propagation step. So this is a more formal definition of the problem. So if I have a graph G, I consider a subset of vertices S, and I will define Pi of S, a set of vertices that propagate from S at step I, or the set of monitored vertices. So initially, what I take is a set of vertices monitored by my set S is just the close neighborhood of the set, or the union of the close neighborhood of all vertices in the set. And then I will increment this index here, in this exponent here, and I will denote from P0 or from Pi, I will construct Pi plus 1 by taking a union of close neighborhood. And I will take the close neighborhood of every vertex, which is at the beginning in the set of which is a vertex must be in the previous step to be monitored with this set. I want that the number of vertices in this closed neighborhood in the previous step was at most 1. And this definition, a bit more formal, is interesting for 2 reasons. The first one is that I can define the sets Pi plus 1, and it will be easier. It may be easier for proof then. And it's also interesting because later on I will think about generalization of this problem. And that's and here the only constant that is completely arbitrary is this one here. Okay. So now what is clear is that at some stage, my set Pi, my sequence Pi will stop to increase because it's a subset of a finite set. So at some stage, I get that Pi0 plus 1 is equal to Pi0 for some I0. And then I know it will never change anymore. So I can denote P infinity of S, this biggest set of vertices reached. And we say the set S is a power dominating set of the graph if this end up by monitoring every vertex. So this Pi0 or this P infinity of S is equal to the whole set of vertices. Okay, I hope everything is clear with the definition. And I will continue with heredity. So you must use heredity sometimes. So usually we call heredity when there is some monotonicity when we add or remove some edges or vertices. So one first thing is we observe that domination is a harder problem than coloring. Sorry, the chi of G did not go through here, but in graph coloring, the chromatic number of a graph can only decrease when you remove edges. And the chromatic number of a graph can only also decrease when you remove vertices. It's always easier to color the graph. But domination is a harder problem because, okay, when you remove edges in a graph, the dominating set can only increase because you have the close neighborhood of a vertex is always at least as large. And so you dominate more vertices with the same set of vertices. But when you remove vertices, you can remove a vertex which was forcing you a new special vertex to dominate. So you can decrease the dominating number of the graph, but you can also increase it if you remove a vertex which was very tactical to be put in the set. So power domination is even worse compared to this. So I have only, so here in this new slide, I will consider deleting a vertex and deleting an edge. So when I remove an edge, a vertex from the graph, I pretend I can, so when I remove, I can decrease the power domination number, but by at most 1. For example, here, but I also can increase of unbounded value. So for example, here, if I take this graph here, I put this vertex in the power dominating set. If I have both the dashed vertex and the other vertex, this is a K33, and this graph needs two vertices to be power dominated. I can, from this set of blue vertices, there is no propagation possible because every vertex that is adjacent to one of these two white vertices is adjacent to both. So it's never the case that we can extend the set because no vertex will have at most one neighbor not in the set. But if I remove one of these two vertices, suddenly this becomes a power dominating set because only one vertex is not monitored. So this vertex will propagate to here, or this one, or this one. Okay? So this means so the power domination number of a graph minus a vertex can be it can be less than the power domination number of the initial graph. But it can also be more. And so you have some obvious examples, like in the dominating set, where you move vertex which dominated plenty of vertices. But you also have some more funny examples where actually you could propagate before. You could propagate before, like for this example here, when this vertex is in, this one can propagate here. And then at the next step, these two can propagate, both of them can propagate. If you remove this vertex, this one can propagate here, but it cannot propagate to any of these two. Okay, and when I delete an edge, I have the same phenomenon. So here I take the same graph. If I remove this edge, suddenly this vertex here can propagate to that one because this one becomes the only non-monitored neighbor of this vertex. And if I kept the edge, I could not propagate. And similarly, here, if I remove this edge, this vertex will never become dominated. So there is no monotonicity in any direction with power domination. And this is a bit troublesome for proving some of the upper bounds and some of the lower bounds on the power domination number. There is some, sorry. And okay. So now I will try to describe some general bounds that have been proved for the power domination number. So one first easy claim is that the power domination number of the graph is always at least 1, unless there is no vertex in the graph. And it is always at most a domination number. I can always take a domination number. I have no step of propagation, but things go fine. It means that dominating set is always good. But in a general case, there are some graphs where we cannot do better somehow. So in this example on the left, we observe that the best power dominating set of the graph is necessarily a dominating set. And also it gives us a bound. So what's happening here is for every vertex, for every vertex, if we want to get stuck from the power family. In this graph, we see that it's a special family of graph where every vertex, we take any graph at the beginning, and to every vertex, we attach two new vertices that may either be connected or not. And you see here, every black vertex has two antennas. And what's happening is on any set of 3 here, we need to pick one vertex in the power dominating set. Because if we pick none of, so for example, we take these 3, if we pick none of these 3, then this vertex may be dominated from a neighbor, yes, but none of these 2, and it will always have 2 neighbors not monitored, so it will not be able to propagate. So the Zhao, Kang, and Chang inferred in 2006 that for any connected graph with at least 3 vertices, the power domination number cannot be, so they prove that it can always be at most 1/3 of the vertices, and this is tight for this example here. What I wanted to show is that in this example, indeed, you need to have you need to have at least 1/3 of the vertices to dominate it, and you can always make some construction like this. Okay. The other example is case 3, which is of a bit of a different flavor, but which cannot be extended to an infinite family. Okay, and so with some author, this study on the regular graph was continued, and one first thing is this bound of n/3 can be improved for regular graphs. So first, if we consider cubic graphs, we could prove that every cubic graph. So in a cubic graph, it's simple. Every vertex has 3 neighbors. So every vertex chosen in a power dominating set will dominate at first 3 neighbors. So maybe there could be some redundancy if we choose vertices which are not far apart, but we could prove that we still manage to dominate at least 1/4 of the vertices. I mean, to dominate with at least 1/4 of the vertices, the whole graph. And but this bound is also tight, and this is one example of a graph. There are many graphs where this bound is tight, but this is an example of a graph where it is tight. And the proof of the tightness is a bit similar, because you can just remark that if you take a set of 4 vertices like this, if you don't pick a vertex in the power dominating set among these 4, then you may dominate the 2 extremities, but you will not be able to propagate to the 2 middle ones. Okay, so this is a bound for cubic graphs, and we had some conjecture on regular graphs with a larger degree, but it revealed to be false. So we could not. I could not. Things are not simple we cannot extend this proof to regular graph with a degree different than 3. Okay. So this statement of a structure where we cannot enter in is interesting also in another family of graph, which is the family of planar graph. So this is the example I showed you at the beginning, and I can state something else. I have a special part here of the graph, which you may recognize. In the middle is an octahedron. And the octahedron is, so we're in maximal planar graph, meaning that I want a graph which is planar, so with a planar drawing, but if we add any edge, it does not remain planar. So it means every face must be a triangle, because if we have a C4 as a face, then we can add a diagonal into the C4. And in such graphs, there is a nice conjecture for domination, so I will mention it later, but we can do something similar for power domination. So what I state here is, if I pick a set of vertices outside of the octahedron to power dominate the graph, so for example, I take this one, which is a very large degree, and I have some propagation that happened, but I cannot get inside this small triangle of the octahedron. Again, because every vertex outside has got 2 neighbors inside this triangle. So I cannot get inside. And from this, I can build a family of graphs, which is a bit funny, where which is built especially of octahedrons. So here I have 3 octahedrons. I can complete with many edges so that this becomes a triangular a maximal planar graph. And here, if I try to power dominate this, I must have at least 3 vertices in the power dominating set. Indeed, I must have someone in this part, because otherwise I cannot enter it, someone here and someone here. So I must have at least 3 vertices, and I could extend this construction and show that there exists an infinite family of planar maximal graphs where at least n/6 vertices are required to power dominate it. And we wanted to try to find an upper bound. And so this is what is happening here is similar to what happens for domination. So in domination, if we replace this octahedron with K4, so K4 is a triangle with one vertex in the middle. If I replace this octahedron with a K4, I take a set of K4s. I just plug them, I just connect them with a set of edges so that it becomes a maximal planar graph, never connecting the middle vertex, which cannot. And then I get, for domination, the regular domination, a graph for which I know a dominating set cannot be smaller than n/4, 1/4 of the vertices. And it is conjecture for domination that 1/4 of the vertices is the worst case, meaning that you can always, so there are graphs where we need 1/4 of the vertices, but 1/4 is always enough, meaning that if you take some other construction, you will manage to do it with better than 1/4. But the best known upper bound until now, to my knowledge, is of 1/3 vertices. So we can dominate. We know that we can always dominate a planar graph, a maximal planar graph with 1/3 of the vertices, but the conjecture, the hypothesis most likely bound that of the upper bound for this is 1/4. Maybe you have seen some talks about this. So here we could do something similar with 1/6, and so I will get into some. We try to prove a part of this. So one of the most recent results we've had on this topic is for maximal planar graph. So given a maximal planar graph G, we know that the power domination number of the graph is at most n-2/4. This is some work we did with Antonio Gonzalez and Claire Penara. And the idea is, I just give the idea of the proof quickly now. But what is nice here is, so we wanted to get the 1/4, and we figure out, and what is, kind of funny is the fact that it ended up that it's easier to prove n-2/4 than just n/4. That's maybe what's more interesting in the proof. So I just will stress this out. So at first, we know we have to kill all the octahedrons. Octahedrons are going to get us stuck for propagation. So at the beginning, we just find a set that hits all the octahedra. So everywhere, if we have some octahedra, 2 octahedra with a common vertex, we just pick one of this common vertex, which will dominate these 2, and so on. And somehow, with some basic ideas, it's not very hard to show that we can choose this initial set so that the set of vertices monitored initially, thanks to this, is at least 6 times the number of vertices we get. So we start with this bound, and this 6K, it's good because so for every initial vertex, we dominate 6. So if we have just one such set, n is 6, n-2/4, it's 4/4, so it's exactly 1. So we are happy. Even if there is only one set, if we guarantee that we monitor at least 6 vertices, then we are happy with our bound at the beginning. Okay. So now we've killed all the octahedra, and we've got this this set of vertices which will propagate to some part of the graph, and we want to look at what is left once we have monitored all the vertices we can. So in the graph, we can have some structures of where we do not have any propagation possible. And we will do this. So the idea is now iteratively, we suppose we have an algorithm where we hit all the octahedra. Then every time we choose a vertex which will monitor 4 new vertices if it's possible. So we'll keep this n/4 bound now easily. And we compute the set of monitored vertices and we look when we are stuck, when we cannot choose a vertex which will dominate 4 new vertices, and that's when we will be in trouble for our proof. And we will look at the subgraph of the vertices which are not monitored, and we will either get that it is empty or find a way to monitor 4 new vertices and get a contradiction. Okay, so when I look at this G of this graph induced by the unmonitored vertices, I get no vertex with degree larger than 3. Otherwise, picking it will dominate immediately 4 new vertices. No component of order larger than 4 because I have some propagation possible. And so vertices in the set. And I observe that every vertex in the set of monitored vertices must have 0, 2, or 3 neighbors in the set of non-monitored vertices. Okay, so this is an example of a component of size 5. And if I pick one new, it will monitor the path. So what I get at the end is a set of configurations where I can be stuck. So one configuration, for example, is this one. I have some graph G1. I don't know much, but it's surrounded by monitored vertices. I have some graph G2. And in the middle, I have 3. I cannot have 4 because I will be able to dominate them. I have 3 neighbors, 3 vertices here, not monitored. And there is no propagation possible from the black vertices. You see, because every black vertex sees 2 white vertices. And if I pick one extra vertex here, for example, this one, I do dominate these 3, but I do not dominate 4 new vertices. And we can prove that we have some basic case plus this set of cases where we are stuck with our construction. And in G1 and in G2, there are 2 subgraphs here, which are disconnected somehow. In these 2 subgraphs, many things can happen, but somehow I don't care. So what I will do now is I will still try to monitor all of G1, monitor all of G2, and get happy. So what's happening is, so with these structures here, for example, I have this P3 here that cuts my graph. I can have this P3 here that cuts my graph in 2 parts, G1 and G2. And then I want to monitor this and this, but this inductively can again contain one of these configuration, and I get something like this. So I can monitor this, but not that, and so on. But eventually I get to this makes me a tree of components, of parts of the graph, and eventually every subpart will not contain any of this configuration. So, and now what I can do here is in this configuration is, so I know I can dominate this with my bound n-2/4. I can power dominate this with n-2/4. And now I want to add some vertex somewhere so that I dominate larger parts. And what is nice here, and I announced before, is that this -2 is saving me. Because by the computation, I get n-2/4 here and -2/4. I have to add one vertex, but this -2 will save me. So I will add that vertex. It will dominate all this I get here. And then I add one here. I dominate only 3. It dominates everything. And now the computation is nice because I said I have n-2/4 in G1. I have n-2/4 in G2. So I have my 2 sets. My new set of vertices is completed by one vertex. And then so I have a set S, which is at most n-1 n-2/4 plus n2/4 plus 1. which is equal to n1 plus n2 over 4. And my new graph, I have completed my new graph with the vertices of S1 plus the of G1 plus the vertices of G2 plus at least, 2 or 3 new vertices. So the bound is still remaining true. And it's really this -2, which gives me some liberty to glue G1 on G2. Okay. So sometimes the morality is sometimes trying to prove a harder bound turns out to be, a stronger bound turns out to be easier in this case in particular. And so we managed to get this bound of n-2 over 4, but the question for maximal planar graph G of what is the power domination, the best alpha such that the power domination number of G is at most alpha of V plus O of 1 is an open question. So we know it's between 1/6 from this graph and 1/4 from the proof we just made. We have only one case where this bound is tight, which is drawn here. So it's got a name, a hard name, a triacis tetrahedron, I think. But it is the only case where this bound is tight to our knowledge, on more than 6 vertices. So if you are good with planar graphs, you can try this question. Okay, and so now the more interesting question in this is how to find lower bounds. So I've proved upper bounds. Finding upper bound is just saying, oh, if we construct the graph like this, I know it will power dominate the graph, and so I have some upper bound. Finding lower bounds with power domination is much harder, because with this propagation behavior, we get some trouble to lower bounding the graphs. So you remember with the grid, we have a finite number of vertices. We for the Cartesian product of paths, so we grid with a very long in one direction and short in the other. We remember that just dominating a few lines were sufficient to dominate the whole graph. So this is a bit of a trouble. So, well, yeah, this is just a summary of what I just said. So finding an upper bound is just, it suffices to find a construction. Finding lower bounds is sometimes harder because a given vertex can monitor infinitely many vertices like in a path. And what is nice in here is that in most proofs of lower bound for graphs, you need to use some kind of invariant. And invariant are elegant ways of making proofs, in my opinion. Okay, so I have some. So I will not spend a long time. You see many family of graphs where people wanted to compute a power domination number of the graph. So it started with a square grid, and Dorfling and Henning made a proof for the Cartesian product of path. So we had some work on Cartesian products, on other products like strong products and so on, which I will refer to at some point because this is an example where I know well the invariant. And Chu and Kang made a study on the generalized Peterson graph, but did not manage to find a lower bound in 2010. And you see, and then cylinder story, hexagonal grids, Sierpinski graphs, and triangular grids have been studied. Maybe some more since then. So the bound for the Cartesian product is a bit ugly, but not so much. So if you have Pn times Pm, and you suppose so you should suppose that n is fewer than m, and which is not appearing on my slide, which is not good. And then you can dominate the graph with about n over 4 vertices. So somehow with n over 4 vertices, you manage to dominate 2 lines, and then you propagate through everything. And they proved it by describing the shape of the monitored set. So the monitored set becomes some union of pyramids somehow on the graph. So you have some diagonals involved, and it's not so easy. But so one thing which is I mean, yeah, I stayed for the Cartesian product, but okay, let me go on. I don't know if so. The hypercube is a Cartesian product of K2s, and it's also a nice question because the domination number. But you will tell me it's hard necessarily because the domination number of the hypercube is not well known yet, and but the power domination number of the hypercube is obviously always known. Gamma p of Qn is always no more than gamma of Qn minus 1. But sometimes, I mean, yes, sometimes you have a difference that appears, and the first time it appears is for Q6, so the hypercube of dimension 6. Okay. So we have some nice pictures. So that gives you an idea of why it's not so easy to prove the power domination number of a grid, because once you've taken this vertices here, for example, for this honeycomb mesh, you pick 2 vertices like this, you dominate the 6 blue vertices plus the 2 chosen vertices, and you can see that you have long chains of propagation that slowly cover the whole graph. And so here, with these 2, you need 13 steps of propagation to dominate this whole honeycomb mesh. So you have to check that you power dominate everything, but you also have to check that you have no smaller sets. So that makes the problem quite hard. And you can see that moreover, the sequence is not a continuous sequence. So maybe in this example it is. But you see here, you need to start at the 4th step of propagation. Then you wait for this vertex to be monitored by this chain. And then you can go on the 10th step, 11th step, 9th, 10th, 11th, 12th step, because it propagates in parallel. And here we have a triangular grid. So this is the second result. Here again, you have long chains of propagation to reach the vertices. So at some point you have some pattern in the set of vertices monitored each turn. So here you can see the 13th is a set of makes a line somehow here. Then the 14th makes the next line. Then the 15th next line, and so on. But you have to identify this pattern and describe them to make the proof. And this is not so easy. So, but you have some nice trick to make such proof, and I will show you an example. I mean, I'm basically giving you examples where I contributed because I know them better. But so this is another kind of grid, the king grid called, because it corresponds to the movement of the king on chessboard. And so every vertex has 8 neighbors on that with diagonals included. So when you pick a vertex here, you dominate 9 vertices, the vertex chosen, plus the 8 neighbors. So here, if you play a bit with such a grid, you will figure out that you can make some pattern to dominate the whole grid. So it looks, you make something that looks like that. So you do cover blocks like this set of blocks, 9 vertices blocks, and you want to have a diagonal that will be completely dominated. And thanks to this, you can propagate to everywhere, because every vertex on the rightmost top right border, for example, here, can extend to a neighbor because they have all their bottom left neighbors dominated already. So here, for example, this vertex can propagate here. This one not yet, but this one can propagate here, and so on. So you get to propagate in one direction and the other and simultaneously. And then again, you propagate. You can go this one, and you see that you get a similar pattern that appears, and you will propagate to the graph eventually. So if I want to compute the number of vertices I've picked at the beginning to make this kind of diagonal, it's not very hard. So I cannot, if you believe me, if you just overlap the two blocks, if they overlap only on one by one vertex, I mean on one edge, then it's not enough to propagate because this vertex here will have a not dominated neighbor on the left and on the right, and this will be problematic. So here what's happening is the configuration is you place the blocks so that they overlap on two edges like this, and this means you make 1, 2, 3 steps on one direction plus one on the other. So you have 4 steps between every two vertices. And this is why your the number of vertices you pick is about n plus m, which is the length, I mean the half perimeter over 4, because you move by 4 edges on the square grid each time. Yes? And the -2 is because of the corners. Okay. And now the point is, if you do this, you see that this will propagate to the whole graph. The problem is to prove that this bound is best possible. So I will use an invariant. There is a similar, it's inspired by a small mathematical puzzle, which is known maybe by many of you. On some game where you also have some propagation on a square grid. And the invariant there is a perimeter. So here the perimeter is not exactly a good invariant, but I can count the number of these big blue vertices which I have drawn here. These big blue vertices are all the vertices that have fewer than 8 monitored neighbors. Okay, so the middle ones have all the neighbors monitored once I pick them, so they have 8 of them. And so they are either on the border, and I have at least one unmonitored neighbor, or they are on this side of the board. And in this case, they have fewer than 8 monitored neighbors, but they will not propagate anywhere, so they get stuck. And the idea is every time I've got a propagation happening in my problem, every time this vertex will propagate to a neighbor, this becomes, I have a drawing. This vertex propagates to here. Then this vertex quits the border. It's got 8 neighbors monitored still. And I have one, so I have one removed from this set of blue vertices, and I have one added, which is the green one. Okay. What I can have is I could have, not here, but so every time I remove one, I add one. I can show it's not very difficult to check that when you can have a propagation from someone on the side of the and it could be from someone which is not on the side. It's a little trick to apply. And then the invariant I claim is that the number of vertices in this set will never increase. Okay, because when you propagate to only one neighbor, so it cannot increase. So eventually, so you get this one added, and this red removes. Now at the next step, you add 2, you remove 2, and so on. So eventually, you get this big vertices becomes the whole perimeter of the grid if you manage to do it. And this set did not increase during the process. And at the end, it contains all the vertices of the border, so 2n plus 2m minus 4, because the corner are counted, each corner is counted twice. And the set at the beginning, when you choose your power dominating set, every vertex dominated 9 vertices and was not in the set, so every vertex you picked contributed to the set by 8. And this gives me another bound, but obviously you see that these two bounds are very similar. So this was enough to prove that, to give nice bounds in most of the cases for the power domination of the king grid. Actually, there are some cases where we don't have the complete proof, but I mean, there is a small gap. You can check this if you are interested, but it's not very easy. And maybe it's that, yeah, okay. So this is the kind of environment that you must have to find a lower bound. And this is somehow nice, but not always easy. So that's the summary. In power domination, my environment was that the number of monitored vertices with a neighbor not monitored is never increasing. And this is not only true, I mean, in the previous case, I had some tricks on the border, but this part is always true. And the problem is at the end of the process, usually you don't have any vertex with no neighbor monitored, with the main neighbor not monitored. So you can do variation on this. You can either find a limitation of these arguments where you have some vertices which remain in the set. So both Penara and Verdon shot in 2018, what they did is they do the same kind of argument, but instead of looking at the border at the end of the process, they stated the border halfway to the process of the process. So when half of the vertices are monitored, what is the size of the border? They prove that it must be at least some value. And from this part, they inferred a number of vertices to be picked at the beginning. Or what I said before, Dorfling and Henning in the first proof for some from some lattice like that, they used the explicit description of the shape of the monitored area. Okay. So I don't know how much I should finish soon, I guess. I just wanted to remark that there are some generalization of this problem. I mentioned it at the beginning. So here you remember maybe this was the definition I stated formally at the beginning. I said the only constant here is this one here. So what happens if we replace this one by another value, say a k? And so I replace here 1 by k, and I say, what does that mean? It means that a vertex here can propagate not necessarily only to one vertex, but to at most k, meaning that if, so here if I take k equal 2, it means that every vertex may propagate to all of its neighbors if there are at most k, so here 2, not monitored yet. So here, for example, this vertex has 2 neighbors not monitored, top one and bottom one. And so this one can propagate no. So in usual power domination, this is completely stuck. No, this one can propagate here. And then from this one can propagate also on top or on right, these two, and so on. So you have a new whole bunch of problems to consider. And so this problem is what is nice in this generalization is that indeed it generalizes power domination, where k is 1, it's a power domination number. If k is 0, it is a usual domination number. And we get some similar behavior from the power domination and the domination with this. So for example, the critical graphs. So if you remember, my critical graphs before were some graph where to every vertex was added two leaves somehow. And here again, you can do the same with k plus 1 crowns, meaning that you add k plus 1 vertices to every vertex. You get some general bounds, and the algorithms are similar on trees and so on. And so quickly, so this is the k plus 1 crown. So meaning that if you take any graph H and you add k plus 1 leaves to each of its vertices, then you cannot propagate. So here you have the same fact that you must pick all the vertices of H to dominate the graph, to power dominate the graph. And so the bound n of gamma pk is at most n over k plus 2. And somehow this may remind you of the bound for gamma. Pk, when k is 0, is a usual domination, and you get n over 2. So the n over 3 that we saw at the beginning is quite natural from this. And it's quite funny also because if you can take any sequence, I mean, what is clear is that if you increase the propagation power, I mean, if you increase the k, you decrease the power domination number because naturally, but any sequence of value, for example, 75532, you can find a graph where the domination number is 7, the power domination number is 5, the 2 power domination number is 5, the 3 power domination number is 3, and so on. You just have to plug the good number of leaves on the vertices. And so we have some general question on products, and so the question becomes very general. And if you know gamma pk of G and gamma pl of H, can we give a bound? Can we know something on gamma p of some function of k and l of G times H for any product? So this is an infinite set of open questions, which is quite usual, quite convenient if you want, but they are not necessarily easy. And so this was studied in 2006. I mean, some generalization can appear. So for the claw-free cubic graph, we knew we had the bound n/4. And so it was improved to non-claw-free, but even though if you keep the claw-free in S, then for k plus 2 regular graphs, this bound extend. And this is, yeah, maybe I didn't give enough example to really illustrate it, but here, if you take a kk plus 3, and you remove one edge between the two extremities, and then you branch to the other. Do I remove one edge? I'm not sure. No, you don't remove any edge. Then you get the cycle, and yeah, okay. And just an extra, I don't know how much time I see Said switch on his camera, meaning I have to finish, isn't
it? Yes, almost finished.
Just one extra definition and I stop. So we also are interested in the propagation radius. So the propagation radius is simply the number of propagation steps you need to reach the wood graph. So remember for the hexagonal grid and so on, we had some propagation radius of 13. So I just, you don't need to read this, but the radius is, so you have this 1 plus because I want to stick with the radius of the graph in general. But the number is minimum I where you dominate the wood graph. So for example, here, the propagation radius, so it's 14 somehow, because I do 1 plus this 13, which is the largest number on the picture. And what is nice, let me skip. So we have also some heredity and not heredity on the propagation radius. It's not clear, I mean, the radius of the graph is equal to 1 if and only if the power dominating set is actually a dominating set. And if the degree is large enough, then the radius is equal to the radius of the graph and the power propagation radius. So I just have a nice picture and I stop.
Okay.
I just say that it is not clear that, I mean, you can have a very small dominating set. For any a non k, I have a graph where I need even the k power domination number is equal to 1. I mean, here in this graph, I need only one vertex to dominate everything, but the radius can be as large as I want. And so here, this vertex will propagate to here, then this one can propagate to this 3, if k is 3, this one to 3, but you need to go all the way like this before you get to the end. So I think, I don't know what is my effect. Either I have the propagation or I have a similarity of this graph with a peacock. Okay, I finished. Thank you for your attention.
Nice. Oh, thank you very much, Paul, for a nice presentation. Very nice. Is there any question or remarks, comments?
Paul, thank you very much for your nice presentation.
I hope it was understandable. It's not easy to see if I go too fast or too slow by video conference, but
okay. Paul, just I want to know that whether the power domination number for Corona product has studied. I think it's not very difficult.
So I think it's related to the I'm not sure. I don't remember precisely for the Corona product, so maybe there is something to be done here. I know there are, yeah, I can't tell you. I don't remember having seen any of this. So I did a survey recently, so I should have noticed it. But so I can tell you that in 2020 there was no such study.
Okay. Okay. No, thank you so much. Okay, there is no question? Please thank Paul again. Thank you so much for
Thank
accepting
you,
the
Power.
invitation. Okay, I think the workshop now ends, and I hope the lecture were useful for all of the participants. And I hope all of you be success and healthy. And thank you, Hamid, for organizing. And let me to say bye-bye to all of the participants. Thank you, Hamid.
We are looking forward all of you in the next event.
Hopefully. Thank you so much. Thank
Good
you,
luck.
Bal. Thank you.